Hi, welcome to another episode of Everything and Anything. I'm Mike, and today we'll be talking about Pythagoras Theorem. While you may be wondering why are we talking about something so simple? Well, stay till the end and you understand why. Now, to be clear, what is Pythagoras Theorem? Well, it is an elegant expression, a squared plus b squared equals to c squared. And we've seen it in high school, middle school, it's not a difficult concept. It's just basically the sides of a right angle triangle, and you square them and you get the square of the hypotenuse of that triangle. Now, before we move on, I just want to have a little feeling of the history here. Pythagoras Theorem, well, it's not exactly created by the man himself, Pythagoras, who lived about 560 BC. He created a following, a secret group called the Pythagoreans, and there's no concrete evidence that Pythagoras himself devised or rather discovered this ratio between the sides of an orthogonal triangle. It may have been one of his followers that attributed this credit to him, but we never know for sure. Of course, in parallel civilizations, the Babylonians, for instance, also had some form of discovery of this so-called Pythagoras theorem, which is honestly is just the ratios between the orthogonal triangle, right? So yeah, in our context, the history of how the name of the Pythagoras theorem came about is not really that important for us. From now on, we just take it as a convention and call it the Pythagoras theorem. Now, before we can even move on to the applications, maybe we want to do a little proof of the theorem. A lot of people don't actually think about how this theorem actually works. They just take it as what the textbook or the teacher says: a squared equals to b squared equals plus b squared equals to c squared. Well, I'll show you one, although there are over 300-400 of them. Just search out the internet. There's really a lot of them. Now, the one I'm going to show you is a very simple, elegant proof by a 12-year-old boy, to be honest. A 12-year-old boy came up with this proof, and a simple proof. Well, the 12-year-old boy is not me, to be frank. It's not me. I wish I was, but no. He's by the man himself, the great mind of the 20th century, Albert Einstein. When he was 12, and we know Einstein was smart, right? When he was 12, he came out with this proof using simple geometry that honestly any middle school student would have learned about. Come, let me show you how he did it. Okay, now we'll talk about the proof of the Pythagoras theorem by Einstein. First, he devised a circle, and within that circle a triangle, with the hypotenuse being the diameter of the circle, and all points of the triangle touching the circle. We know from simple geometry that the angle indicated must be a right angle. Now, he drew a line down from the top of the triangle to the base of the triangle and divided the triangle into two smaller triangles, the green triangle and the orange triangle. Now your job now here is to prove that all three triangles, the outline triangle, the green triangle, as well as the orange triangle, are similar. And I'm going to give you a hint. To prove similar triangles, at least two angles must be the same for each triangle. Now, take a moment to pause the video and think about it. Well, I trust that you've thought about it. Now let's move on to view the explanation. Now the triangle in question, I already drew out the right angle triangles here. Now we already knew that one of the angle is the same in all three triangles, and that is the right angle, the 90 degrees, right? Now just look at, focus on the read out the big triangle now. We know that one of the angle, the unknown angle, must be theta, and the other one must be alpha. What else do we know? We also know that theta plus alpha must be 90 degrees because a triangle can only have 180 degrees, right? Now, if that is the case, then let's look at the orange triangle just now, the medium one. That means that angle there must be alpha, correct? Because 90 degrees and theta 180 degrees minus both of that angle gives you alpha there, and similarly we have a theta there. Now, continuing from the theorem of the similar triangles, we have the fact that if you square any similar side of the any similar triangle, it will be proportional to its area. Now, since the area of this small triangle plus the area of the medium triangle, which is the orange and the green just now, will give you the area of the large triangle, which is the red outer line, that follows that the hypotenuse of the small triangle squared plus the hypotenuse of the medium triangle squared equals the hypotenuse of the large triangle squared. And here we are, a squared plus b squared equals c squared, proved. Now, take a moment, pause the screen if you don't really quite get it, and I can ask in the comment about it. We'll move on to the applications of the Pythagoras Theorem. And now, this is the reason why I chose Einstein's proof for Pythagoras Theorem, because this Pythagoras Theorem itself actually influenced one of the greatest minds with its greatest work, the Special Relativity in 1905, and that of time dilation. We'll take a look. The famous thought experiment by Einstein, that if there is an observer A in the train and an observer B on the platform, and the train is moving at velocity v towards the right, with the width of the train being w, train moving, right? So how will time pass differently from the observer A and observer B if the guy A in the train shoots a beam from one side of the train to another side of the train widthwise? Now, simply for the guy in the train, it doesn't matter, because he will not feel the movement, the velocity v of the train. Imagine if you throw a ball straight up in the train, will you still catch the ball straight down? Exactly, that's how it works, right? So to the guy A, the time, the beam that he shot from the widthwise, the time, we just call it delta t prime. Delta being the change in change, and t prime being the time experienced by this observer A, is basically just twice the width w divided by c. It's a simple middle school concept. Time equals to distance divided by speed, and time is, and that's time, right? So, and then we have light. It's a constant being, as you can see that 299792458 blah blah blah. However, I need to remind you one thing. Although it seems so simple that we say that time is a constant, actually a lot of work has been put into establishing that time is that light is a constant. And for that, you may want to look into the whole argument of whether light needs an ether to travel, whether light can travel at infinite speed, and as well as Maxwell's unification of electromagnetic wave. Now, we'll move on to the observer B. For the observer B, the distance traveled by the train is, now we first talk about the distance traveled by the train. We don't talk about time first, okay? Now the train is moving right at velocity v. Now, we know that there is a time variable delta t. Now this delta t, remember, doesn't have a t prime, because this delta t is with respect to the person on the platform. So it's a different variable t, okay? Now this delta t, we don't know. We're just assigning it a random variable called delta t. We know that the distance traveled must be delta t times v. And the reason why I put divided by 2 is because I just wanted to show using these curly brackets that the half of the distance traveled. This is because we will be applying Pythagoras Theorem later. As you can see, we have two right angled triangle here. Right. Now, we'll move on to distance covered by the light. Distance covered by the light from the point of the observer is not as simple as the one in the train, because in the train you don't need to care about the velocity towards the right, right? But for the person on the platform, you do, and the light will actually travel. Look at the red lines. Yeah, you actually travel in this slanted way and form a triangle. Yeah. So, and we know that because the distance is actually equals to the velocity, or rather the speed of light, multiplied by this empty variable t, which we don't know yet, okay, delta t. So speed times time equals to distance, correct? Simple middle school physics concept. Remember this. But it also can be expressed with Pythagoras Theorem. It's twice of that red line, right? The twice of it. And it's just v delta t over 2 squared plus w squared. Look, this is just the Pythagoras Theorem. Although we introduce a lot of variables, the essence is the same. And we equate this c delta t. And now we're going to solve it, okay? The math, it's actually, although there's a lot of symbols, it's actually very simple. Just this whole equation is basically a rearrangement. We move the 2 over to the left side, and then we square both sides, take out the root. And now we expand the left side and as we move the right side over, the v delta t over 2, we move it over and we expand it out. Then we do some rearrangement by factorizing out delta t squared. Then we have in the bracket what we left on the left side, and the right side doesn't change, right? And some simple rearrangement by dividing what's in the bracket from the left side to the right side, so that we can isolate delta t. Now the whole point of all the rearrangement is here to isolate delta t, and then we square root both sides, right? When we square root both sides, we get, of course, remember, we always get positive and negative roots. But in this case, we'll only take the positive roots because change in time must be positive. Or at least at this level, it must be positive. And we get the expression 2w over square root c squared minus v squared. Now, simple math, factorize out the c squared in the denominator, and we get 2w over c and 1 over this whole crazy expression, right? And this expression, this thing in the bracket is very important. This is known as the Lorentz factor and conventionally denoted as gamma. This is very important. The whole concept of time dilation lies on this gamma, and if you read the paper of Special Relativity, the gamma is one of the most important thing in that paper. And there we have it. Since we have already proven that 2w over c equals to delta t prime, which is for the observer A in the train, we have come to a relationship between the time experienced by the observer B and that of the time experienced by the observer A in the train. And that relation is gamma. Now I'll move on to the applications of time dilation. Well, one example will be the GPS with a satellite in the sky and you on the Earth trying to determine a location, and we need to take into account special relativity. The satellite is analogous to the train, and you on the Earth is just like the observer on the platform. Now you need to take into account the different time experienced by you and the satellite. But of course, that's not the whole picture. You also need to take into account general relativity. Then only then can you actually get a precise location. Now we've come to the end of this episode. The point of this lecture, or rather video, is to tell you that something so simple as a Pythagoras theorem can actually underpin so many applications and discoveries, well over thousands of years since its conception, and I believe thousands of years more. Well, I hope that you learned a thing or two today, and I strongly urge you to go and find out more if you're interested in relativity and whatnot. Thank you for watching, and I'll see you in the next one. Bye.